Bismillah ar-Rahman ar-Rahim. So, in today's lecture, we are going to talk about, to continue our discussion on Verilog. Okay, and today we are going to talk about how to convert a basically a finite state machine with data path together, okay, to a Verilog, synthesizable Verilog code. And I mean, there are actually two ways to do that, and I'm going to discuss one way of them, which is the better way, okay? The better way, which is basically an implicit Verilog module, okay? طيب, أول حاجة, let us remember the GCD calculator, if you remember, okay? I just made a tiny change to the algorithm so that it becomes a little bit easier for us to implement. It's not that difficult to implement, but even if I use the version that we had before, it's not that difficult. But I mean, this version basically assumes that you have two data input ports, one for X and one for Y. Okay, and you can read them in parallel. You can read X and Y in parallel. So let's remember how the GCD works first. First of all, I set up my ready. This is the initial state here. You can see I set up my ready to 0. Okay, this is a little tiny register, 1-bit register, which is a flip-flop. Okay. I set it to 0 and then move to state S0, okay? And then in state S0, I check go. If go is, again, I'm looking for a positive edge on go. So both this state and this state looks for a positive edge on go, okay? So once I receive a positive edge on go, means that I need to also, again, reset my ready to 0. This one was initial state, and this one is for when you run the loop again, okay? When you enter the loop again to calculate the GCD, all right? So I do these assignments in parallel, 3 assignments in parallel, and this is, notice that this is a what? This is a mealy box, okay? Mealy assignment, okay? Or mealy register transfer, which means it is only going to happen if go is 1. And it is going to happen when you are in state S1, okay? In state S1, and go is 1. I'm going to have these mealy control signals sent to the data path to enable these register transfers, okay? So after that, I move to the state S2, okay? And in S2, what I'm going to do is, first of all, I check if X equals Y. If X equals Y, then this is the end of my GCD calculation. I know that, for example, my output is X, let's say, okay? My output is X. So I know that X contains my output, X or Y. It doesn't matter, actually, because they are equal. So I set my ready to 1 as a mealy box here, okay? Conditional box. One of the mistakes that that you did in the quiz, yeah, Shabab, I noticed that this is a common mistake, okay? Is that you use a mealy box right after a state box. This is wrong. Okay, a mealy box right after a state box. A mealy box needs to be preceded by a decision box, okay? It must be preceded by a decision box, otherwise it has no business to appear, okay? So if X equals Y, I set ready to 1, and I wait for the next positive edge on go, right? Once go has a positive edge, I reset ready to 0, and then start reading the other pair, and then calculate the GCD. Otherwise, if it's not equal to Y, X does not equal Y, I check if X greater than Y, then I subtract Y from X, and solve the result in X, and then come back here and do that again. else I subtract X from Y and store the result in Y, and then do that again. All right, this is the algorithm that we covered last time. So the objective of today's lecture is to convert this algorithm to an implicit Verilog module, okay? To an implicit Verilog module. Pay attention, please. Let me bring the mic closer to me, okay? Pay attention and take a mental image of this state machine, okay? I'm going to switch to Atom, okay? And I will create a new file here. Okay. Where is the a new file? Let's say new, and let's call it module. This is, I mean, again, you are writing Verilog, so anything in Verilog must be placed inside what? Inside a module, okay? A module, okay? Module, and then you give it a name. Of course, the name is going to be the same name as the file name. Let me just give it a save so that we get color coding, yeah? So this is gcd dot v, yeah? So now for the inputs and outputs, or the ports, the input output ports, what do we have? We have, first of all, we know that this is a sequential circuit, so we must have the clock, and we must have a reset. Okay, these are the minimum inputs. Okay, also must have we know that we must have go as an input. All right.
Data
Any other input?
in. Data in.
DN1 and DN2. Remember that we had two data input ports for X and Y. Okay, we don't need to time multiplex now. We can read them in parallel. Okay, and that's it, right? That's it. I can also produce, for example, if you want, I can produce data out to be a combinational output. Okay, combinational output as that is connected directly to X, for example. Okay. Now I need to declare my or define my input. So these are the three inputs are clock. These are just wires, clock and reset and go, right? I can also generate parameter so that I fix. I don't need to fix. Let me call it n here. And let's have n as 8 by default, okay? N is going to be the width of the data input and output, which is the width of X and Y, all right? So I have here my my inputs also, inputs that are n minus 1 all the way to 0, dn1 and dn2, all right? And I have an output that is actually n minus 1 all the way to 0, and it is d out. And internally as my state, I have a register called X and a register called Y, and both of them are n minus 1 bits, yeah? X and Y, yeah? And also, I would like to connect we forgot one, by the way, one output. What was the output, by the way? Data ready, yeah, ready. Said ready is not connected, okay? So I'm going to have it like an output here, all right? So it is just a single output, okay, ready, all right? Now, for D out, I can say, I can use a continuous assignment statement, D out, okay, which is basically tied up to X all the time, okay? However, it depends on ready, okay? Whether the data is valid or not depends on ready, okay? Now, this takes care of the output. Okay. I mean the combinational output. Right. We have an always block here, since we have a what we call a sequential circuit. Okay, the sequential circuit must be sensitive to what? To the
Positive edge.
positive edge of the clock. Yeah, positive edge of the clock or negative edge of the clock, whichever you like. But when you write a test bench for this, you use the other form. Okay, if you use the positive edge and they use negative edge on the test bench, or vice versa. So let's use the positive edge here. Positive edge of what? Of clock. Yeah. And then I have a begin, an end, and also, not in case, it's end. Okay, an end module, so that I don't forget. Yeah. Before I proceed, also I have to declare some what we call local parameters, local param, for the state names. Yeah, the state names, the state symbols, and I give them codes. Yeah, SI, and its value is, for example, 0, and S0, its value is we can just have 1. It doesn't matter, actually. The value is going to be so let me go back to the and see how many states, to the picture, and see how many states do we have. 1, 2, 3, 4. That's it. Four states. Yeah. S0 is 1 and S2. That's it. All right. So this is like listing, or this is for state assignment. Yeah, state assignment. I'm using this for state assignment. Let me be consistent here. And then the first statement in my always block is to check for, because the reset signal has the highest power and the highest what we call control over all the other signals. I must check if reset is pushed. Reset is pushed, the button is pushed, then I should go to the initial state, right? Now, how do I maintain my state? I have to also create another register for the state. Yeah. And how many bits does this register have?
2 bits.
I have basically 4 states, right? 4 states, it means
2 bits.
2-bit. Yeah. I can barely hear you, by the way. It's your voice is far away. So 2-bit is enough, actually, for the state. Yeah. So if reset is activated, then my state is going to be SI. That is step number 1. Okay. Else, if reset is not activated, and what do I do? Let me just have a begin and end here. Okay, because I want to be sure that I surround this block by a begin and end. Now, I have to, in order to know what to do, I have to know what is the present state, right? If the present state, for example, is S initial, then I need to reset my ready, right? Okay, so I have a register called ready, actually, and this is, let's call this as let's call this output port, let's call it data ready. Okay, data ready. Okay, and this is data ready, and this data ready is actually assigned data ready to be ready, and ready itself is going to be a register which is part of the state of the circuit. Ready. Okay, so if you are in state 1, in state SI, then all what you do is you set ready to 0, and then move to the next state, move to the S1, S0. That's all. So you have here a case statement based on the value of the state. Yeah, the state is SI, and what do? you have two things to do.
Assign
Begin.
ready 0.
Yeah, but you have two things to do. Since you have two things to do, then you need to surround it by a begin and end, right? So first of all, you said data ready. The ready itself, ready register has to be set to 0, and what? My state, my next state, yani, okay, is going to be what? S0, right?
S1.
It's S0, not S1. I called it S0 here. Okay?
Excuse me.
It doesn't really matter. I mean, أهم حاجة إنك يعني you be consistent with your naming. Okay, this is one state. Yeah, you have a question?
Yes. Now, shouldn't we put data in the data of ready is 0, and the ready will and the data of ready will be uploaded to the
لا
ready
هو شوف
register.
I'm just executing this as a register transfer. This is a register in Verilog. You don't need to worry about the mechanics. This is the beauty of using an ASM chart. Okay, it just maps one-to-one to Verilog. Okay, so you use the same statement here exactly in Verilog. Okay, so this is statement. When will this statement be executed? When? It will be executed when you are in state SI. Exactly. Only. Okay?
Okay.
And what do we load on ready? What do we load? We load 0. Okay? We load 0. طيب, for S0 now, for state S0, what do? We have actually nothing to do. No assignments whatsoever except that we are going to check go. So there is an if statement here. If statement, and the next state is going to depend on go. So I can say here, without even a begin and end, state is going to be depending on go. If go is 1, look, if go is 1, then I stay in S0. Otherwise, I go to S1. Yeah? Got it? Shabab. And let me just scooch this over so that you can see both. So here, I'm saying if I am in S0, then I check go. If go is 1, then I stay in S0. If go is 1, then I stay in S0. Otherwise, I go to S1. Does this make sense?
Yes.
Okay, so let's do the other one, which is this one now. Can you tell me what is the thing that you are going to do here?
We need to check for go and assign the registers.
Yeah, so will a conditional be more readable than an if statement here?
I think we need a
Yes.
bigger if statement.
If statement is better because you'll only change the state if go is 1. Okay, if go is 1, then you are going to execute these register transfers and then move to state S2. All right. Otherwise, you will stay in S1 without executing any of these transfers. Okay. So we have an if statement here. If go is 1, which means if go, right, then what do? I have begin. Let me just put it in the next line here. Begin and end. How many statements? How many register transfer statements here do I have? 3, right? 3, but I need to also update the state. Yeah. So it's 4 in total. So first of all, my ready is, notice that I'm using what? Non-blocking assignment. Okay, non-blocking assignment. Ready is 0. I'm initializing it to 0. And then X is going to get what? data n1, and y is going to get data n2, and the state is going to be s2. Okay. Otherwise, if go is 0, and nothing to be done here. If go is 0, nothing to be done. So the state will maintain its value, which means that you are going to stay still in S1, right? No need to say that explicitly. You don't need to say else state equals S1, okay? Because it didn't change, okay?
Sorry, but
Yeah.
don't we need to another positive edge of Go to upload Y or to download the data on Y?
Yeah, because all right. So that's what I'm saying here. We are having two data input ports,
Okay.
so we can load them in parallel. Okay, two data input ports, data N1 and data N2. Okay, they are different. If you only have one data input port, then yes, you are right. You have to load X, and then in the next clock cycle you load Y. All right, but here we are assuming for simplicity we have two data input ports. All right.
Okay.
طيب. Next, this is S2 now. S2, what do we do in S2? Look and tell me. We just make it smaller here so that yeah. So in S2, maybe I should show both. Yeah. In S2. In S2, what do we do here? We need basically an if statement.
Conditions.
If, else, if and else, if and an additional else as well. So we have an if statement here. If what? X equals y. Yeah. If X equals y, then I say here two assignments here. What are the two assignments? Ready is 1 and what?
State is 0.
State is 0. Excellent. Excellent. Yeah. So begin and end. I have ready is 1 and state is S0. Okay. طيب. Here I have an else if. Yeah, else if X is greater than Y. You see the beauty of when you are writing an implicit code here, you don't really need to worry about the data path components, as they are going to be synthesized for you by the synthesis tool. Okay, here we are using the greater than operator, and there is going to be an implicit what we call inference of a comparator here. Okay. So if X is greater than Y, then what do I do? Begin. Actually, I don't need a begin and end here, because what? Because basically, because it's just one statement, because I don't need to change the state, right? Yeah, so I just update X minus Y, and then I have a final else, Y. This is going to be valid only when Y is greater than X, right? Y minus X. Yeah. Otherwise, you stay here. Otherwise, you stay in S2. All right. And I can say default whenever you are in any other state. What do? State is initial. You go just to the initial state. I have to have an end, what we call case, yeah? So case must end with end case here. And begin and end actually are already taken care of here. So I have a begin at line 20, which is closed at line 44, and then 46 closes 17. Yeah. and we have an end module. That's it. Now we need to, any question before we move on to the test bench? Fine. So we are going to write a test bench now. Test bench, a simple test bench, just to show the because you know sequential circuits are a little bit more involved. I'm going to show you how to test them and show the waveform. Okay, so I'm going to let me just grab some code from before here. We have the TB, yeah, just to begin with, yani. Yeah, I forgot the time scale. Well, let me just copy that and then say new and save. Let's call it TB, capital letters, TB GCD.v, huh? Yeah. Okay, so it's a test bench for the GCD. What is the GCD file? Yeah, save it. And then I'm going to instantiate it like this. Okay, and also having the data definitions. So go to the, I need to move these up here. Okay, the input becomes what? A register in the test bench, right? And output becomes a wire. And I need to define n as a parameter, yeah? Actually, this should have been a wire, yeah? This is the output. Let me go back to GCD again. Yeah, should have been a wire. What is EBGCD? Yeah. So for this one here, we need a parameter. N. Let's have it as 8. Okay, 8-bit. Which is the default basically, so we don't need to supply it. And we remove, for instantiation, we remove basically the module keyword, and let's give it a name GCD0. And we are just hooking up the ports in the same order as defined in the module. Okay, yani the binding here is by order, not by names. طيب. Now the clock business. We need to. Did I say to you last time that test bench is not synthesizable, Shabab? So test bench is only for simulation purposes. That's it. So we cannot synthesize the content of test benches. They are mainly and primarily for simulation purposes. Let me have an indent on this. Okay. Yeah. So the clock business, first of all, I have to have an always block that is running every, let's say, I don't know, 5 time units. Okay, and its main business is to complement the clock. That's it. It just complements the clock every 5 time units. So the clock period is going to be 10 time units. Okay, and then I have my initial block. All right, begin and end. Now this won't work. This won't work unless you have to initialize your clock to a value. Yeah. Otherwise, it will generate X's for the clock. Okay. Don't cares. Yeah. So you have the first statement here is to set the clock to something, to, for example, let's say 1. Okay. Let's start at the beginning of the clock, or 0. Let's say. Let's start with the 0. Okay. Also, we would like to reset our circuit at the beginning. So reset is, by the way, reset is it synchronous or asynchronous? Reset. Let me go back to the GCD and ask you this question. Is reset synchronous or asynchronous input?
Asynchronous.
Asynchronous. Why is it asynchronous?
Because if it's and if reset is 1, then the circuit will be clear regardless of the clock.
Is this what you see here? Is this what's in
Uh,
front of you? Can you just
No,
look?
it is synchronous
It is synchronous. Yes,
because
definitely.
it's inside the always
Yeah.
block.
Yeah, because basically because we are only checking this if statement here is checking reset only at the positive edge of the clock. So at any point other than the positive edge of the clock, we do not check reset, right? So we will give our reset a 1 here, okay? But then it won't have an effect until the positive edge of the clock, right? So I'm going to wait for the positive edge, pause edge of clock. All right, I think I need to put it inside the parentheses. And probably the @ sign is outside here, yeah. So at this point, I know that reset is going to be activated, so I just need to wait for the next negative edge of the clock, okay, to bring it down to 0. Why am I doing this? Because I want to avoid timing violations, yeah? I'm giving it a complete period to be applied before the clock, before the active edge by half a period, and after the active edge by half a period, okay? So at exactly the first negative edge, I'm going to pull down my reset, deactivating my reset to 0. Now, the reset, what does it do? The reset, the only thing that reset does is that it resets the state, which is the present state, to the initial state, okay? So after this, I should see that the initial state is initial, okay? And then I'm going to at every actually I can apply it here as well. So let's also have a go here, a 1, okay? All right, so go initially is 1, okay? Go initially is 1. All right, here I'm going to apply go to be 0, and then at the next negative edge, I'm going to apply go equals 1. What happens? When is the positive edge of go going to happen? Exactly at this negative edge. Okay, because go was 0 and then it went up to 1. But when will it have an effect? And the next, and the positive edge that succeeds this negative edge. Okay. All right. So, excuse me. So, in addition to go equals 1, in addition to having go, having a positive edge in go, I should also, per the algorithm, you can see here, per the algorithm, I can, I have to also set up my dns. Yeah, dns should be set up. Yeah. dn is, yeah. Let's just have dn1 being, for example, 15, and dn 2 being I don't know, maybe 20. Okay, the GCD here is what? 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20 we expect it to be 5, right? 5. GCD is 5, isn't it? 15 is 3 times 5, and 20 is 4 times 5. So it's 5 basically. All right. So how many clock cycles do I need in order to know that my calculation is finished? I need to wait for what? For a positive edge on ready. Once I get a positive edge on ready, I know that my algorithm finished, right? So I can say here at pause edge on ready. All right, which is one of the actually data ready. It's called data ready in my test bench. Yeah. Once you get a positive edge on ready on data ready, then I can do what? I just wait for a couple of time units and then finish the simulation. All right, you guys got it? Except that I need to also use the dump. So I want to generate a waveform so that we examine it. Yeah. I'm commenting that. Let's call it GCD.pcd. All right. And the test bench is called TB GCD. This is the module name. Just copy the module name. Oh, GCD. You just copy this and paste it in here. Yeah. Also, I forgot to your modules are supposed to have the same time scale, so I forgot to have this time scale here. All right. Now we're almost done. So let's switch to the shell and try to compile Verilog my GCD.v and my TB GCD.v. Oh, we have an error. Excellent. Okay, so let's go to line 30 and see if any one of you can observe this error or not. So line 30 in the test bench. What is line 30? The error is silly, actually. You guys do you know what the error is?
Second end.
Yeah, end module, actually. We didn't end the
Yes.
module. Okay, and then that's the only error we have. Okay, unfortunately. So A dot out now. What will it do? It will generate the waveform, hopefully. Hopefully it will finish. Okay. It is looping forever. So there is an error here. Okay, so let me just quit. Control D. I'll see. And I just tried everything. Help. There is finish. Yeah, finish. Okay. All right. So what you can do here is, instead of waiting for data ready to be a positive edge, this is what was causing the number of cycles to an infinite loop. Okay, so we need to debug. So I'm going to run for 100 time units and then finish. All right. Let me recompile and then run. This is now it's done. Okay. So I'm going to open up my waveform viewer, which is GTK wave. And yeah, I'm going to actually drag and drop. Not this. Verilog code. No, not this. Yeah, this one. And it is gcd.vcd. Yeah, value change dump. Yeah. So this is the test bench that we have. Let me just put this, and then this. I just wanted to make sure that the data is in a correct order. Okay, data N1. So yeah, maybe it's because no, no mount. Okay, yeah, as it was zoomed in very much. Okay, so you can see here that reset is 1 at the beginning, and we are applying a reset exactly at the positive edge. You can see that, and then at the next negative edge, it comes back. All right, and then it is 0 for the rest of the simulation. Okay, let's also view the state. So you can drill down to the tb.gcd and click on the gcd 0 instance, and we can also view the state. Yeah. So we are going to state 0, 0, which is state initial, and then going to state 0, 1, and then we stay in 0, 1 forever. You see here, forever. So let's see what is wrong in our module here, ECD. In our module, in state S0, which is 1, okay, S0, we stay forever. So here, state, okay. Am I writing the conditional correctly here? I think it is taking the value of go. Maybe I need to surround it by parentheses here. And to be absolutely sure. So I'm checking if go equals to 1, okay, then go to S0, otherwise you go to S1. As per what? As per the logic here. So let's see if we detect a 1 on a 0 on go at this state. So at this state here, go, where is go? Yeah, we have an actually an active edge, a positive edge on go, and it is actually okay. Oh, I see. Okay. See. So we are changing go here. Okay, the positive edge on go is changing within the cycle, within the clock cycle, so it's not detected. All right, it is actually not detected. Let me see, 0. So go here equals 0, and then here it equals 1. Okay, it's possible that go, the positive edge of go did not get detected. Let me just update the test bench slightly here. Okay, and add a little bit of just a dummy negative edge here. Nothing to do. And then add another one where we actually, this is not needed, and this is not needed as well, okay? Where we set go to be equal to 1, yeah? And also this. Okay. All right. Right. Let us recompile and try again. Okay. Let's see that and reload. You see, now it's working. That's why this is what I suspected. You should give it more than one clock cycle to change, okay? To change. So basically, you need go to be detected, يعني as a 0 first in the positive edge, and then as a 1 in the next edge, okay? So you can see that the GCD actually D out is detected to be or is calculated to be 5 at the positive edge, and ready has been actually asserted high. Okay, ready has been asserted high at this cycle. Okay, so now we can go back and again change our code to be dynamic. So I can remove this actually and change this to just to 10 and try again. Okay, it works now. Okay. Remember that fixing the errors, especially the logical errors, is one of the most challenging problems. So inshallah, in the next video, I'm going to try my best to record the video offline to show you how to make a comprehensive test bench for the GCD module, so that you know how to make a comprehensive test bench for sequential circuits as well. But for now, I think the video is, the class is over, and I need to stop and ask you to do attendance, yeah? Let me stop recording.